in regards to questions or anything in general? Nope. Okay. Um, gonna moving on. So this week we're gonna deal with carbonyl chemistry. So basically, it's the carbon that is double bonded with an oxygen, and we see variation of it. I kept this slide as it is, not because that I'm getting lazy or anything, but it's just that it's just the same kind of theme going over and over, but with a slightly different reaction. It's basically what I'm trying to say right here. So coming up the third thing, I'm going to talk about reactivity. This maybe also will cover like next week or so because of the material that is about carboxylic acid reaction. But basically, when you look at the reactivity, here is illustrating the electrophilicity because as you can imagine, if you do have some sort of nucleophilic substitution, you're going to look at the electrophilicity too, because you're going to have something that kind of having some sort of polarized positive charge so that the nucleophile can attack. But what other thing do you notice about increasing the electrophilicity of the carbonyl? It's something that we talked about last week. I know this is not like multiple choice questions. It's more like something that you think about in terms of the nucleophilicity. And what you can imagine, and this is just a slide from one of the questions that we have done before, that is related to acid catalysis. And what acid does is to help the substitution, the nucleophilic substitution. And what does it do is by creating a better leaving group. So in relating to that, you can put it in that perspective of the electrophilicity right here. That means that in all the nucleophilic substitution is necessary for a to an electrophile to be able to leave whatever that they're connecting to the carbonyl carbon, right? So what is telling you right here in terms of the electrophilicity is also indicative of how well are they able to leave that carbonyl carbon. You can imagine that something that is like a halogen, like chlorine, would be more able to leave easily than something that is oxygen because like other group 7 has abundance of outermost electron and they kind of hang out and be pretty stable by their own as in an ion. Whereas if compared to the other oxygen species, it may not be less able, like as capable to do so. So this is just one of the questions is actually from the Kaplan book, and hopefully that you guys have read it. And it talks about one of the property of reactivity. In this is in terms of acidity. And I'm gonna give you guys 2 minutes to do these questions. Wait, Rashina already got the answer already. So I don't know if we need 2 minutes, but let's see if other people got the same answer too. So I don't know if everyone got getting the same answer. Here, how I would try to approach the questions is that I look into where the electrons are pulling away to. Is so the blue arrow basically indicating all the electronegative species, and they are well known as their property to pull or kind of grab the electron. So with the pi bonds electron being pulled towards the oxygen on the top, so you can imagine that the hydrogen on the B position is being destabilized. Whereas you look at the position C, the hydrogen on position C, although it's also destabilized, but it is not as strong as being surrounded by two carbonyl oxygen around it. And because of that, like the one in the position B actually have a pK of around 13. Whereas if you think about just like oxygen, just like water or any methanol kind of species, their pK is usually like around 16. So I'm gonna keep moving. And in terms of one of the key thing is really about the solvent. So as I have started with this slide, and again, all the OChem with like OChem reaction is mostly about these things: the nucleophilicity, leaving group solvent, and heat. And here is just talking about aldol reaction, and if you have read through the material, that's retroaldol reactions, where if you implement it the other way around with the aldol product and feed it a lot more basic solution into it, it's going to revert the process. So that's why the solvent often matter. And here I'm gonna have another questions that is also I extracted because it is a prime example to illustrate how the solvent helps or does not help. And I will also give you guys 2 minutes to work on this one. So let's see. This question talks about benzaldehyde reacting with acetone. So first of the things that we could be asked and to think about is which one is the nucleophile? Do you guys think it's the benzaldehyde or the acetone itself? I mean, Rashina has the answer, which is the acetone being the nucleophile. Do you guys agree? Mm. Yeah. So what I would think is because usually in these carbonyl chemistry, usually they attack the one that is usually a carbonyl carbon. And it happens that because of the very stabilized benzene ring, And just having one hydrogen on the outside with the carbonyl carbon is pretty much electronegative on that carbonyl carbon is pretty hard for him. And what happened with that polarized positive charge on the carbonyl carbon on the benzaldehyde as the electrophile, then it makes the acetone more capable to react towards the benzaldehyde. And what happened right here is that we want to speed up the reaction. And focus on, if we look in the carbonyl chemistry, in order to help the leaving group leave, you can make the electrophile to be more positive, right? Or you can make the electrophile slightly more negative, so that it's drawing it more towards grabbing the attacking the electrophile. So I am checking if everyone is still following with me. So with acetone being the nucleophile, do you think that it wants to be more negative or positive to become a better nucleophile? Remember that last time when we look over the nucleophilicity, we determined that nucleophile is better when it is negative charge, which Hannah, you got it. So to make it a more negative charge, how would you do it? You put it with the acid, but then the acid, we're gonna protonate the species, making it more positive, right? So the other way around is to add the base so that you pull a proton away and making your nucleophile more negative. And then, yeah, you can think about that. You can think about like Lewis base, like because Lewis base kind of concept is based about which one is the electron donor and electron acceptor. So to make it more negatively charged, it's gonna be more capable to attack that benzaldehyde, which is a slightly polarized positive. And then moving on, then here is another concept about the kinetic and thermodynamic. So I'm gonna give you guys one moment to think about which one would be a kinetic product, or uh, the left one or the right one is the kinetic, or the left or the right one is the thermodynamic. Um, oh, so Hannah, you said that you know what they mean. When you say they, you're saying the kinetic and thermodynamic, right? Okay. Yeah, you don't know how to tell by the difference. And that is what we are about to go over. So here shows two possible outcomes when you deprotonate the species. And you can see that there's two options, the hydrogen on the left and the hydrogen that is bonded to a tertiary carbon. And here's the thing that I want you guys to kind of think about whenever you encounter these questions. So when you look over these structure, think about the temperature. What is the reaction is occurred? Usually it's given to you. They will tell you that they give a lot of heat, or they making the reaction to go at 200 degrees Celsius, something like that. And another thing to think about is the stability of the structures. Which one would be more stable? So by looking at the left one and the right one, which one do you think is more stable and why? The left one. Arshina said the left one. Very nice. Yeah, I mean, so you can think about from the distribution of the electron. If you're gonna have the electron distributed with some source of electrons, which is from the oxygen with the negative charge, along with the methyl group, which can also be a source of electron, then it makes the double bond more stable in that sense. How about the energy? Oh, why is the left one more stable? Because to make the double bond more stable, you want to bond it with sources that has electrons. So for example, the methyl group, although it does not have a charge, it does have electrons around it. And that electron crowd along the methyl group will also contribute to the double bond stability. Does it make sense? Yeah, no problem. So that is why it's more stable. And when the compound become more stable, what do you think about the energy level? Is it higher or is it lower? Lower, yeah, because it's stable. Like, it's almost like physics. When you put something at a higher place, the potential energy is going to be higher. When you put something lower, lower. So, the more stable it is, the energy level is going to be lower. And but let's think about how the reaction occurs. You have to deprotonate one of the protons, well, one of the hydrogen, pulling them off from this reactant in order to produce our product, right? So think about the steric hindrance. Which one would be more difficult to produce? The left one or the right one? Oh, I mean like in the product, the left product would be more difficult to produce or the right product would be more difficult to produce. Okay, Hannah said is because we have two Hannah, um, so I don't know. Hannah B. Okay, let's do that. Hannah B said the left product would be more difficult to produce. So the left one has to be pulled by taking the proton that is connected to the methyl group. And because the methyl group is kind of blocking the accessibility to that proton, yes, that one would be more difficult to produce. And what do you think about the activation energy? With like a higher steric hindrance, what do you think about the activation energy? With greater steric hindrance, will it be greater activation energy or lower greater activation energy? Yeah, higher, higher. Very nice, very nice. So it is greater activation energy, but remind you that temperature is related to activation energy, and I went over that in Jan Chem with the activation energy equation. Um, hold on, give me one moment. I don't know what did I do. So temperature is related to activation energy by the sense that the higher the temperature it is, the more collision there are within the molecules themselves. So therefore, it the higher the temperature, it's gonna bring more energy to produce the product that would requires a harder time to achieve with greater steric hindrance. But in turns, that product it happened to also be the product that is with a lower energy level and with greater stability. So with that, you can summarize it by all of these, which we just talked about. And if you just kind of entangle little pieces by pieces, you'll recognize that the one that we all have been talking about that has lower stability, that has greater stability, lower energy level, greater steric hindrance though, and greater activation energy required, and thus favor at higher temperature, is the same one, is the left product, that is the thermodynamic species. Whereas the right one, that is easier to achieve, it although it has a lower steric hindrance, thus requiring lower activation energy, it does not provide as much stability and does not have as low of an energy level compared to the thermodynamic species on the left. Okay, so thermodynamic favors whatever that is greater stability, lower energy level, but sometimes it will occur more steric hindrance, thus favor when you give them heat, which means the temperature. Okay, so this is in the slides, and think about it really a lot more, okay? And here we're gonna go through these questions really quickly. It talks about this reaction, enamine to imine. And what kind of reaction is that? I'm probably gonna give you one moment, like 1 minute, because it's pretty straightforward, I think. So Rashina said it's B, and I just put it right there because I was a little bit concerned if people only refer tetramerization as something that talks about alcohol, like the eno and the keto reaction. So it does not only include the keto-eno reactions, it also includes enamine and imine, which the reason that I brought it up right here is because tautomerization is also a sense of thermodynamic versus kinetic product competition. So this all the same thing that we just talked about applies right here. Like the temperature, the stability, the energy level, steric hindrance, activation energy. I think the picture cut it out with the Y. But how could you think about which one is the thermodynamic, which one is the kinetic? Remember that we have been talking about the same thing quite often since the beginning of today's class. Um, Rashina said that enamine is thermal. Why do you think so?
Just because of the position of the double bond, it's more stable.
Yeah, but why does that make with the nitrogen? Why does that make the double bond more stable? That's one keyword which we talked about a little bit earlier. Is the ability to hold electron. So basically, the electronegativity with nitrogen being stronger So meaning that it is more capable to hold on that electron from the double bond, making it more stable. And when things is more stable, just by that, you can immediately categorize it as the thermodynamic species. So Hannah, I'm not sure if you're following along or you're getting confused, but let me know if you need a little bit more help, okay? Oh, okay. I'm sorry. Um, I just got myself tripped up. I mean because nitrogen is more capable to hold on those pi bond electron, so the imine is the thermodynamic one. The enamine actually is the kinetic one because imine is more stable. Rashina, I'm sorry that I may have confused you too.
No, that's okay. I was just guessing. So the one on the right is actually the thermodynamic,
Yeah,
more favorable structure.
it is more favorable structure, allowing more stability due to the ability of nitrogen to hold on the double bond electron. Correct. Yeah.
I have a question. So basically, the NC double bond would be more stable than the CC double bond, basically.
NC double bond will be more stable because yes, in this case it is because nitrogen it is more electron withdrawing. It's more able to hold the electron than compared to the carbon itself. Okay, so
Okay.
it's the same when you look at enol and keto. Ketone it will be more favorable than the enol. Mm.
Would this have to do with like electronegativity? Because like N is more electronegative.
Yes, it's the same concept. Electronegativity is just referring to the ability of the species or the element itself to hold on that electron. It's the same idea. Mm. You got it. Very nice. And the last thing about the other reactions about the keto,
What's
aldehyde.
the question? What was the answer to the last question?
Oh, the question. This one.
Yeah.
I think I thought you got it right. It's
Oh,
the
total. Yeah, I thought. Yeah, you didn't
yeah,
say
yeah, yeah,
the answer.
yeah.
Okay.
Very nice.
Tautomerization.
Okay. So the only thing that I would note right here is the strength of the oxidative agent and also the reducing reagent right here. So above I listed all the ones that is oxidizing. Remember that in remember that oh shit. In OChem, when we talk about oxidation, it usually refers to gaining of oxygen or losing hydrogen. So that's two things, gaining oxygen or losing hydrogen. And reduction goes the other way around. Reduction means gaining of hydrogen, losing oxygen. So that is very important. And here is one of the ways to kind of generate that oxidation or reducing or reductions. So all the ones that is above, that's oxidation purposes. All the ones that is below is highlighted as reducing purposes. However, depending on their strength, they will reach to a different endpoint. So in the ones that you're having strong oxidizing reagent like hydrogen peroxide, um, the potassium manganese, permanganate, chromate, dichromate, silver oxide, and anything, it will gonna generate the alcohol from the alcohol all the way to the carboxylic acid. If it is not like bonded to probably two other hydrogen, then it will become a ketone. So depending on what are the remaining group, with that carbon that is bonded to the alcohol group. It can become a ketone or it can become an acid. But for PCC, which you commonly will see on MCAT, it is categorized as a weak oxidating reagent. So that means that it can only goes up to ketone or aldehyde, no acid. Just remember no acid, okay? And then for the reducing reagent, that's two type. And again, for the strong one, you can go all the way down from acid to the alcohol. However, when you have the weak one, no acid again, doesn't do anything to the acid. And so the key thing here is if you have weak oxidizing or reducing reagent, no acid product for weak oxidizing reagent. And if it is reducing reagent and it's weak, also have no reaction with the acid itself. Then I will go on to giving you guys the questions. Trying to be on time today.
I have a question. When you
Yes.
say like the acid, you're talking about carboxylic acid, right?
Yes, absolutely. Everything here is carbonyl. So I'm gonna give you guys 10 minutes, 6 questions. So let's meet around 44, 45. Let's do 45. Okay.
I have a quick question.
Yeah.
So for question number 2, when it says, which of the following groups present on the reactants is not present on the product, are they talking about the product directly after step 1 or at the very end of the reaction?
You mean, okay, which of the functional group presented on the reactants are not in the product?
Yeah, like because it's talking about during the first step. Is it talking about the product right after step 1 or the very end product?
I think it is only the step 1.
Okay, thank you. I just wanted to clarify.
Mm-hmm. All right, so I'm trying to make sure that we don't go way over time as we did next time. Oh, last time, I mean. So I would begin to share my screen again. Let's see. Okay, do you guys see it? I hope you do see it. Yeah. Okay. So I when I go over things, it's very important that just focus on grabbing the main idea, which means that don't panic when you don't recognize things that you're not familiar with, because usually they wouldn't test you on things that you are not totally familiar with. We just have to apply related concepts. So what I did here, I kind of go over and I identify the DIM, and they gave you a quick background about what it is. And then second paragraph, it talks about a bunch of spectroscopic techniques. So I might put over that because just in case that they're testing me on NR, I know where I'm gonna look for. And they also talk about the inhibitory potential with IC50 value. Is a value that is almost like what's that called? The half bind, where like the binding site is half filled, like all of the half of the binding site is filled. Basically, is what that means. Um, and then the third paragraph, when I look over it, I just see compound A, most potent, okay. And then they use another technique, X-ray crystallography, and then I'm like, okay. And then they say compound 8, and then they do a mutation. And usually whenever they say mutation, I'm like, okay. I will be highlighting it just in case I need to go over, like go back to the passage and without getting lost. And then the second page shows me the figured, so reaction, I guess. And then when I jumped, so actually I started doing all the questions when you guys started doing your question too. So that's why I was like, okay, let me look over what question you're talking about. So this is basically can be a well standalone questions. So even if you don't know anything about the passage, we should be able to do it. And what do you guys got?
Yeah, I said B.
So you both said B, which is great. And just reminder for like one key things, acid, the strength of the acid is determined by how stable the stability of the anion formed, right? And that is mentioned in the GenChem section. If you're not familiar, you can go back and check it out. So acetic acid, because you can see that chloride, so meaning it is halogen, very stable, and then also very stable as a group 7 member, and then SO4, also very stable. So there you go. And the next one is talks about the first step of figure 1. So let's copy and paste figure 1 right here. Figure 1, and then talks about the first step, crop image. No, okay, crop image. There we go. So it talks about which functional group. So basically, it's just functional group that we are looking for. We need to compare which one is not in the product. Cool. So let's see what functional group we have on the left. We have a halogen, bromide, okay. And then we have amine, okay. And then we have the aldehyde on the second reactant. Oh, Rashina said B, aldehyde. Cool. So let's see if this aldehyde is not on the right-hand side, the compound on the right-hand side. So if you check out, you also have bromide, amine down in the bottom, another amine, another bromide, and then carboxylic group. So carboxylic acid is out, amine out, in aromatic ring, so much on both sides. So out, so aldehyde seems to be reasonable answers. Then we get through it. Okay, next one. So next one takes a little bit of basic biochem questions. And compound A, this is what I'm talking about when they talk about mutation, because I kind of get this instinct later on that they might test it. So you can see that that's why I highlighted Y87, and it decreased because change of property probably. So Y stand for what? Tyrosine, yay. So tyrosine. So if we look at tyrosine, what is tyrosine? Tyrosine is aromatic group, tyrosine aromatic. So we want something that is also aromatic. And so is that how I remember? Like phenylalanine, no, tryptophan. There we go. So FYW. And then I got phenylalanine. And if you can just look at the root of the word too, it tells you they're aromatic because of the phenol, right? So that is another way that we can solve the questions. Even though
Where did you guys get tyrosine from?
Oh, passage. Because Y is stand for tyrosine in short. So that is something that within the biochem you need to remember.
I never knew that.
And also the one letter code for each of the amino acid.
I never knew that. Okay, thank you.
Wait, I have a question. So I was thinking like, because it started out, so tyrosine is like polar, and the reason why I picked C is because threonine is also polar, but can you like explain why it would be phenylalanine and not like, what is it, threonine?
Yeah, because here is a pi stacking interaction, and you can't do pi stacking with polar because there's no pi bond.
Yeah, so it's pi stacking is like stacking of the pi bonds.
So when you
phenylalanine has like pi bonds, and so does compound A.
Is it like anything aromatic that has pi bonds? Or
yeah, but threonine doesn't have any pi bonds. That's why it wouldn't be threonine.
I would say aromatic with double bond, you know. It's very strict with aromaticity rules that to kind of talks about which one is aromatic, because there are multiple factors that you have to consider. You have to count how many pi bonds are there and how many electrons are there. So let me see. Hold on, give me one moment.
Okay.
Back right here. Aromaticity is defined by the following. And I wouldn't bother to memorize everything because I don't think that they're necessarily gonna test it. So it's different in terms of whether it is like ring versus aromaticity.
Yeah, and threonine is not aromatic. I think you were confusing it with tyrosine.
Yeah, I did confuse it, yeah.
I mean, also, like, they're asking for pi stacking, but, like, if they were asking for something else, like threonine and tyrosine, like, both have alcohol groups, so, like, that, I mean, I could see how, like, that's important. Like you could make that connection. But since it's talking about pi stacking, the like alcohol groups don't really matter. So you just had to look for the aromaticity part.
Yeah. Okay. So basically pi stacking just means like the whole like conjugated and aromatic, basically, right? Or like
under certain requirement. Let me just
Okay.
be a little bit stringent with that because I did have experience being picked on not being stringent on my definition.
Okay.
Yeah, but regardless of the definition, doesn't really matter. But remember that only phenylalanine, so F stands for phenylalanine. Okay, so now I know. Rashina, you need to put that amino acid on your study schedule.
Yeah, I have to like write out all the amino acids and like glycolysis. It's like a lot of things I have to like start writing out.
Yeah, I understand totally. Tryptophan. I don't even remember how to spell tryptophan. I just remember because this W looks like two mountains upside down, and I got tripped over. I don't
So
know.
the only amino acids with letters are the aromatic ones, or do they all have letters?
Oh, they do all have letters.
Oh, okay.
No joke. No joke.
Yeah, there's like 20 of them, yeah.
Yeah.
I never knew that. I don't know why.
Oh my
Or maybe
god.
I did and maybe I just forgot and I didn't study it hard enough. That's crazy.
I got told by my professor one time. He told me that I'm not a biochem major if I don't know about my amino acid, and he said that that is like English major don't know alphabets, and I'm like, cool, learn it.
Oh my God, that's so harsh.
Yeah, but I don't know. Oh, I cried a little, but it's okay. Oh, Hannah, do you have a question? I saw you unmute.
Yeah, sorry. I have a follow-up question to just clarify the amino acid notation. So, like, this one is like, Y87. Let's say you substitute, yeah, so it's Y87. And so how you'd represent that shift to alanine, right, would be Y87A.
Correct.
And that means, like, yeah, that would writing it like that would indicate that, like, the tyrosine got changed to alanine. That's how you do that, right? Or no?
Oh, yes.
Okay.
That is the right way to say. Yeah, you're totally right. I think I have no more additional comment. I would just put it as a note for everyone right here that usually the one that is written on the leftmost position indicate it is the original amino acid. Okay, I just abbreviate that as AA right here. And then the second position usually is a number indicating the number of amino acid on that peptide chain. And then the third position is the mutated amino acid, what it is. Okay, so hopefully that helps. Okay, colored, and then colored. Cool. Okay, moving on. Fourth questions. They want to reduce the rate. Okay, cool. And then the second step. Okay, we'll have to pay attention with the question. The second step. Second step of the reaction in figure 1. Which of the following would not decrease? Okay, so not decrease means increase. Compound 2 formation according to the Chatelier's principle. Okay, cool. Then copy, paste. Okay, and then it is the second step. We're going to look at second step. Cool. Okay, so here's our second step. All right. So send it backward. Still not seeing. Fine. Here, it talks about option A. Let me see if you guys have any answers. C. So decreasing the concentration of compound 2. So compound 2 is actually our product. So if we decreased the concentration of compound 2 is going to drive all of those reactions to form more compound 2. So that means that it's going to increase the rate. Yeah, and here talking not decrease, that means increase. AKA, let me AKA, okay. Okay, so that means that we got to this. Yeah, Anna, you're correct. I'm not sure, do anyone, oh, Rashina is at B. Why? Let's see.
I don't know, because I figured, I don't know, I think maybe I misunderstood it, but I figured if you could decrease the initial reactants, you would have less product to even move forward with the second step. But I mean, I guess I should have just only looked at the second step. And then, so the answer is C, decrease the concentration of compound 2, which would increase the rate. Wait, I'm a little confused about this question and just the wording.
It is tricky. They always try to trick you. That is just the thing. That is just bluntly obvious, right? So when they say not decrease, it means increased. Then I just follow and grabs onto whatever that increased. And Le Chatelier principle say that increase for rate, then you need to increase your reactant.
That makes sense. When you change it to increase, it makes sense.
Yep. So always try to make sure reading the question very carefully. They read question very carefully. Very tricky. Okay. All right. So 5th. So this is a question that I added because since last week we did a question on radioactive decay, I just like, yeah, no way. So this question asked about alpha decay. So let me remind you that alpha decay meaning that you're taking helium, which has 4 atomic mass, right? 4 atomic mass with 2 proton. Okay, proton. And here we have 32p. So 32 is the atomic mass, right? And then 15 is the proton number. Proton number, I'm just going to write proton number. Okay, so phosphorus minus this, decay meaning away, right? So let me put it, so minus this, that's why we minus this. And then we lead it towards to aluminum, which has 32 minus 4 is 28 atomic mass and also 13 proton number. Oh. Okay. Transparent. Cool. Okay. Let me see. Oh. But this one you guys have C. Let me see. Yeah, so this is C, huh? Remember that this proton number defines the nature of that element, okay? So that's why it is C. And we got
So I have a question. So 28 is the atomic number, or is that the number, is that the mass number?
Atomic number is the, atomic mass, I mean. Sorry, AM, atomic mass I'm talking about. Sorry.
28, I'm sorry, 28 is the atomic number?
Atomic mass.
Oh, that's the mass. Okay.
AM. That was what I was trying to say.
Okay. I think I needed a periodic table for this question.
Oh, they do have it. Yeah.
Oh,
So
I have
it's
a question.
provided.
Sorry,
Yeah.
I have a
Yeah,
question on that last one.
Mhm.
I just know alpha decay is just like A minus 4 and Z minus 2. Is that
what?
A minus, like, I just know that alpha decay, like I learned it as like, it's just like A minus 4 and then Z minus 2. I mean, I got the right answer.
Yeah, it's the same
You know
thing.
if that's okay.
Yeah.
And like Z is the proton number, right?
Yeah.
Okay.
Yeah. It's the same thing.
Okay, thank you. I didn't know if
Yeah.
that was like a universal.
No worries. No worries. I think you got it. That's fine. And then the last question, a student set up a TLC. So this is also something that we talked about in previous sections. So TLC.
Wait, I just have a question. I'm so sorry about the last question because I think that whole alpha decay stuff I need to brush up. It's like thing. So when like Hannah Moss said, so I think, did you say A minus 4 and Z minus 2? So A is the atomic number minus 4, and then Z minus 2 is moving back 2 spaces on the periodic table.
Z is the proton number. Yeah, because
Z is
whenever
atomic
you
mass.
move
I mean,
proton,
what is Z is atomic number? Atomic number, yeah.
yeah, it's the same. Atomic number is proton number.
Okay, thank you.
Okay. And then here talks about TLC. Remember that the mobile phase and the solid phase, no, the mobile phase and stationary phase are different in the way that the polarity is different. So here they talks about, they already gave it to you that the mobile phase is nonpolar. Then I'm like, cool. That means that our stationary phase is polar, huh? So okay. And then we look into the reaction. The reaction talks about carboxylation of benzene. So, oh my goodness. So what does it mean when you add the carboxylation, when you are done with the carboxylation, does benzene get more polar or non-polar?
It would get more polar.
Yeah, because you think about the carboxylation, you have CO2, and whenever you get something that is electronegative into something, which benzene is obviously nonpolar because of that aromatic ring, and no electronegative at all, no electronegativity species. Electronegative species meaning like all the group 7, NO, F, yeah, NOF. Okay. So when you're adding oxygen towards something that only have carbon, and also this only have carbon and hydrogen, that means that it's super nonpolar, no electronegative species, very, very nonpolar. That is gonna make it slightly more polar. Okay. So our product, which is polar, reactant, nonpolar, and silica plate, stationary, it's gonna attract our product, right? When our product is gonna adhere to the stationary phase more, it's not gonna move as much. So what is gonna be carried onto the mobile phase and making further distance to achieve a higher RF value would be our friendly non-polar reactant, right? So any clarification that I need to make? So it is A, polar. Excellent.
So
Guys, do you have a question? Okay.
Let me stop the recording because we are starting to upload on YouTube and things just get really long to be uploaded, you know?